So in this video, I want to go over with you a discussion of continuing our discussion on colligative properties. And last time we talked about this, the fact that when you have something dissolved or solute dissolved, in particular if you have a non-volatile electrolyte. Now remember, non-volatile just simply means that the solute is basically does not go into the vapor state very easily. So it has it basically does not evaporate very well. That's what we mean by non-volatile. And non-electrolyte, of course, is going to be something that does not contain ions. And so the vapor pressure of a solution containing a non-volatile non-electrolyte is always lower than the vapor pressure of the pure solvent. And so this is expressed in Raoult's law, where we see that the vapor pressure of the solvent will equal the mole fraction of the solvent present times the vapor pressure of the pure solvent. Now, we can express this in terms of lowering, pressure lowering, and that's what we have here. So basically, the change in vapor pressure for the solvent will be dependent or proportional to the mole fraction of solute. And so we're going to have mole fraction of solute times the vapor pressure of pure solvent, and that would actually give us the amount of lowering or the change in vapor pressure. Now, I want to discuss briefly part of the reason for this, and this comes from the fact that in a pure solvent, as we see here, we have, once equilibrium is reached, and this is going to be basically will generate the equilibrium of particles leaving the solution and going into vapor phase when the rate of that is equivalent to the rate of particles from the vapor phase coming back into the solution. Once that takes place, we're said to have reached equilibrium, and that will occur at a particular temperature and generate a particular vapor pressure. And there'll be a certain vapor pressure that will exist for the pure solvent. Now, when this happens, basically going from the solvent into the gas phase increases the entropy is part of the reason that this takes place. And the overall entropy of the system is increased. Now, when we have a solution, the overall entropy of the solution is already larger than that of the pure solvent. And so for a solution where the entropy of the solution here is already higher than the entropy of the pure solvent, then we have less vapor pressure because fewer particles have to go into the gas phase in order to achieve the same overall entropy. And so this is the explanation for the why of the lowering of the vapor pressure. So for the entropy of this system, the solution system, to be equivalent to the entropy of the pure solvent system, we already have a higher contribution from the solution because of the increase in entropy here. And so we don't have to evaporate as many to achieve the same level of entropy. And so again, that's just the overall description of why. Now I wanted to talk or go through some problems using Raoult's law to find the change in pressure. And so this problem from our text is find the vapor pressure lowering when 10 mils of glycerol is added to 500 mils of water at 50 degrees Celsius. And then so at this temperature, we're given the vapor pressure of water, pure water, right? And that would be our P0, and its density. And then we're also given the density of glycerol also at that temperature. And so to solve this problem, we need to calculate the mole fraction of glycerol because that is the mole fraction of our solute. And so remember, the change in vapor pressure of the solvent is going to be the the mole fraction of the solute, which is this guy, times the vapor pressure of the pure solvent, which is water. Okay, so we need to find To find our mole fraction, we're going to need to find the moles of glycerol, and we're also going to need to find moles of water. So we will need to find moles of glycerol and moles of H2O. And then we'll basically find the mole fraction of glycerol by taking the moles of glycerol and divide by the total number of moles, which will be glycerol plus the H2O. And then we'll finally multiply that times the vapor pressure of pure water, and we can calculate the amount of vapor pressure lowering. So we start off with calculating the moles of our glycerol. And so we get that from 10 mils of C3H8O3. We're going to multiply that times our density, 1.26 grams of C3H8O3, and that is per 1 mil of the same substance. And then we're going to multiply that times the molar mass, so 1 mole of C3H8O3 is equivalent to 92.09 grams. And so if we carry out this calculation, we get 0.137 moles of our C3H8O3 glycerol. All right, now to get our moles of water, we've got 500 mils. We're given the density of that as 0.988. Of H2O. And then we're going to multiply that times the molar mass, divide by 1 mole is 18.02 grams H2O. We can see our grams of H2O are going to cancel out, our mils of H2O are going to cancel out, and we get 27.4 moles of H2O. Now our mole fraction of glycerol is equal to our 0.137 moles divided by 0.137 plus 27.4 moles. Remember, this is a mole fraction, so we get the unitless number. It's a fraction, 0.00498. And then we can solve for our delta P for our water. It's going to equal to 0.00498 times our 92.5 torr, and that will equal to 0.461 torr. Now, if we wanted to see what the new pressure would be, we could just basically subtract this away from our 92.5, and we would actually get the new vapor pressure of water based on this amount of this 10 mils of glycerol being mixed with the water. All right, now I want to move on and talk about boiling point elevation. And so here we are told that basically boil a solution, and remember a solution is a solute plus solvent, and a solution will boil at a higher temperature than the pure solvent. This colligative property, boiling point elevation namely, is a result of a lowering of vapor pressure, which we just previously discussed. Now, the boiling point elevation is proportional to the molality of the solution. And so we can represent that here as the change in boiling point temperature is equal to our molality, which is given here, times a molal boiling point elevation constant for the solvent. So if we were talking about an aqueous solution, this would be Kb for water. If it were talking about some other solvent, it would be Kb for whatever the solvent was. Now, we can represent this graphically, and what we see here is basically the solid lines represent for the pure solvent. The dashed lines are what is happening when we dissolve a non-volatile non-electrolyte in our solution. And what we see is basically the phase diagram changes. And so the way the phase diagram changes is to the dashed lines that we see here and here. Now, in essence, what we see when we look at our vapor pressure decreasing, or the lowering of the vapor pressure, is actually seen here. Right? So if we look at this and we look at this, we basically have a decrease in the vapor pressure by a certain amount, and that's what we see going from here to here. That depends on the amount of solute present in solution. We also see that this, because of this change, this corresponds to our elevation in the boiling point. So that's where we get our boiling point elevation. Now, similarly, however, though, we see not only does this part of the phase curve change, this part of the phase curve changes over here. Okay, and so what we see then is our next colligative property is we get a freezing point depression. So for pure solvent, we have a freezing point here. If we add a solute and make a solution of the pure solvent, we actually get a lowering of the freezing point, and the lowering would basically be going in this direction. And so that's what we have down here. And that would be our freezing point depression, which we'll talk about here in the next slide. So a solution always freezes at a lower temperature than the pure solvent. The freezing point depression is also proportional to the molality. And of course, we now also have a molal freezing point depression constant, and that would be for the solvent. And so it's given in this form. This Kf is this guy. This is the molality of our solute in solution. And remember, molality is going to be moles of solute per kilogram of solvent. Okay. So given in the next slide are some examples of different solvents. And you can see down here, they're given for water. It's one we oftentimes pay attention to because we have, we often will make aqueous solutions in lab. And so here we have the constants, the boiling point elevation constant, the freezing point depression constant. And the particular thing I want to point you, and I apologize, this slide is just a little bit off, but basically the units here are going to be in degrees Celsius per molal, which is this lowercase m. And that same is true for both of these guys, would be the units of these constants. And so that would be important to keep in mind when you're doing a problem on one of these things, which we will do here. So you have, in this problem from the text, you have 1 kilogram of ethylene glycol, which is basically the antifreeze component of antifreeze. And so this is something that's particularly comes in handy on a day like today. And we're adding this 1 kilogram of ethylene glycol to basically 4,450 grams of water in our car's radiator, right? This would be 4.45 kilograms of water. And then we're asked, what are the boiling and freezing points of the solution? And so again, we come up with a plan for this. We're going to find the molality of the solution. And from the molality, we're going to calculate the boiling point elevation and the freezing point depression. And so we start off here with our mass of solute. We're going to use our molecular weight. We're going to convert that into moles of solute, right? Because we need moles of solute. Again, remember, we've got moles of solute per kilograms of solvent. That gives us this molality. And so from the molality, we'll just go and multiply the constants to get the boiling point elevation and the freezing constant to get the freezing point depression. And we can then calculate the new boiling points and freezing points of our solution. So let's do this. So we're going to start off with our kilogram. And basically we know that 1 kilogram is 1,000 grams. And so we have 1,000 grams of our ethylene glycol. And we want to convert that into moles. So we're going to multiply by 1 mole is equivalent to 62.07 grams of our ethylene glycol. And I'm sorry, that's 2. And if we carry out the calculation, we're going to get 16.1 moles of our ethylene glycol. Okay, now to calculate molality, we just need to divide this by our kilograms of water. So that will equal to 16.1, moles per 4.45 kilograms of solvent. To carry out this calculation, we're going to get 3.62 molal of our ethylene glycol. Okay, now for our boiling point elevation, we calculate our delta T B, and that will be our 3.62 molal times our constant, which we look up on that table from the previous slide, which is 0.512 degrees Celsius per molal. Molals will cancel out, and we will get 1.85 degrees Celsius. And then to get our new boiling point, we're going to take our original boiling point of the pure solvent, and we will add our change, and so we get 101.85 degrees Celsius. That would be our elevated boiling point. And to get our delta TF, we're going to do the same thing. 3.62 molal times, now here we're going to use our freezing point depression constant, which is 1.86 degrees Celsius per molal. That gives us a 6.74 degrees Celsius depression. And then to get our freezing point, our new freezing point, we're going to take 0 degrees Celsius, and we will subtract this 6.73, and we get a negative 6.73 degrees Celsius. So this would be our new boiling point. This would be our new freezing point. Now, the last subject that I want to talk about in this little video is to talk about osmosis. And I'm actually going to drop the calculations from the lecture. I won't cover that on an exam. Just for sake of time, I'm going to drop those. But I do want you to at least hear about and have a basic understanding of what this osmotic pressure is. This is also a colligative property that arises from solute particles dissolved in a solution. But what we find in osmosis is a movement of solvent particles. So for osmosis to take place, what we will need is a semi-permeable membrane, and the semi-permeable membrane means that it is permeable to solvent, but not solute. And that's what we mean by semi-permeable. Now, when we have a membrane present and we have two different concentrations of solution, the solvent will always flow from a more dilute solution to a more concentrated. And this makes sense if you think about this is a low concentration, let me come back here. A more dilute solution has a higher amount of solvent present per unit volume, and the more concentrated solution has a lower concentration of solvent. So really, this may seem a little counterintuitive when we start to get into thinking about it, but really it's not. The solvent is the only thing that can move through the membrane, and it actually is flowing from a higher solvent concentration, not solute, solvent concentration to a low solvent concentration. But when we talk about this in terms of solute, more concentrated is high solute, and more dilute is low solute. And so sometimes this might not make sense because we're basically going to have flow of solvent. It's going to go from here to here. And that seems to be counterintuitive because we're going from low to high. But that's low solute, not low solvent. Low solute equals high solvent, and high solute equals low. So high solute equals low solvent. And so the reality is we're moving from high solvent to low solvent. But when we talk about it, we will talk about it in terms of solute concentrations, right? So we're going to go from low solute concentration to high. So right here, right, from low solute to high solute. Now, this movement generates what is known as osmotic pressure. And basically, that's the pressure that must be applied to prevent the movement of solvent. So if we have a system, then we can actually measure the pressure that's caused by this osmotic flow, and we call this capital pi, and it's expressed in terms of molarity, the gas constant, and the temperature in Kelvin. Now, I'm not going to do calculations with it. They're not that difficult. It's just for sake of time. I'm not going to go over it, but I do want to give you a graphical explanation of this osmotic pressure. So basically, shown in this figure, we have our pure solvent on one side here, and we have our solution on the other side. And so what we have just described in the previous slide is that if we have a semi-permeable membrane that allows solute to pass, so here solute is blue, solute can pass through the membrane, but solute cannot. It's too big. It cannot pass, right? So this cannot take place. Now, that's what we mean by semi-permeable membrane. So this means the only thing that can pass through the membrane is solvent. So solvent can pass through, and solvent will move in which direction? Well, if there's pure solvent here and solution over here, it will move in the direction of the solution because it will go from high concentration of solvent over here to lower concentration of solvent over here. But however, in terms of concentration of solute, we have 0 concentration of solute over here, and let's say we had 1 molar concentration of solute over here. So the flow is going to be from the 0 molar toward the 1 molar. And the flow will generate basically a pressure. The pressure will be equivalent to the height of this column. So if this is open to air, the pressure that this exerts basically will be dependent on this column of solution here. But we could measure the osmotic pressure if we were to take a little piston and put it right here, and we pushed it down. The force that it would take to do this is called the osmotic pressure. So the pressure, the force required to push this down is the osmotic pressure. And so what we would be doing is we would be forcing solution or forcing solvent to go back through here. And then we could measure it in that way. And the key things to keep in mind here is we're going to go from low concentration of solute to high concentration of solute. That is the direction the flow will always be. The pressure then will be pushing on the solution side. Now, sometimes you could have 2 different solutions. So like over here, if we had a 0.1 molar solution, and over here we had a 1 molar solution, the flow will still be in that direction. It will go from low concentration of solute to high concentration of solute, and it would still flow in this direction, okay? And that's basically a graphical description of osmotic pressure.